Hey guys, Mr. Wood back here in another lesson. We're continuing now chapter 5. It's certainly not a bad idea if you're not watching this until after the chapter 1 through 4 test, but we got to keep moving. And so we're into chapter 5 now. Okay, here we go. Jokes. I think I told you those. Okay, here we go. Why would Snow White make a good judge? Because she's the fairest in all the land. That's what good judges are, if they're fair. What kind of horse only comes out at Halloween? A nightmare. And how do you make a skeleton laugh? You tickle its funny bone. So there you go. Those are the jokes. Kind of stupid. Okay, so we're back where we were in chapter 5. We're really doing a lot of review. We talked in our last lesson, we went over Boyle's law, P1 times V1 equals P2 times V2. Pressure goes up, volume goes down. And again, I think everything on this lesson is going to be kind of review, but it's important that we go over that, which will lead us into later in the chapter. Okay, so back to where we were. Okay, so this is a problem we did, and we went through that, and we said that did not obey Boyle's law because the pressure times volume in the first condition didn't equal the pressure times volume in the second, and we kind of led into something we'll talk about later. If something has a stronger intermolecular force, like ammonia, because of the hydrogen bonding, it's not going to behave like an ideal gas. So, okay, now the next thing is going to be the relationship between volume and temperature. So this guy named Charles, he noted the relationship between temperature and a corresponding volume. And you can look at the data, and he's plotted it before, or plotted it there below, but where the temperature of a substance is a measure of the average molecular motion, which is something we're going to talk about here. The higher the temperature, the higher the molecular velocity. So what he's saying is that temperature is going up, volume's going up. And then was the introduction of the Kelvin scale, which I think is actually on our formula sheet. You can always see the little picture of me, but the Kelvin Celsius, again, on the back, it's right there, if you can see that. So they'll definitely expect, they being AP will expect us to use this. But Kelvin is equal to Celsius plus 273, and all the problems with temperature that we're going to be doing in this chapter, we want to do them in kelvins. And so here's the logic that little kind of looks like the Greek letter alpha. It's proportional to, but volume is proportional to temperature. So what that is saying, it's different than pressure and volume. This is saying as temperature goes up, volume goes up. And so what you end up with is this, or what is called Charles' law. And you never will need to go through the derivation here or remember that. Sorry about that little interruption. I'm just going to close the door so it'll be quiet. But this is actually going to be part of the combined gas law, where the volume and the temperature, how they're related. Okay, so we'll do this problem. In the one place where mistakes are made on this is to not get the temperatures into Kelvin. So let's do this problem. And again, this is a problem that you guys could have done from first year Chem. Okay, so again, but I'm still going to do the same thing that I did before. And first of all, so what we did back on the first gas law is we said that the pressure goes up, the volume goes down. They are indirectly related, is what they would say. And here is the first gas law, and you'll never need to know the name of that, but that is called Boyle's law. Well, this gas law is saying that as temperature goes up, volume goes up. And that makes sense. If the temperature goes up, the molecules are moving more. They would want to expand. They'd want to take up more space. And so here is our second gas law. And really, and we're going to talk about a third one here in a second, which will be pressure and temperature. But these are going to all be put into what's called the combined gas law, which you guys might have remembered from first year Chem. But again, I'm still doing this problem that was in the notes. I'm going to do the same thing that I will really recommend you do really all year long, and that is to write out everything it says. So it says that the volume is 452 mils. So I'm just listing, labeling everything. It says that the temperature is 22 degrees Celsius. And you got to remember here, whatever the temperature, you always, if it's not in Kelvin, you got to get it into Kelvin. So Kelvin is equal to degrees Celsius plus 273. So 22 plus 273 is 295. And then it says it is heated to 187. So here's a T2. It is up at 187. So I'm going to take 187 plus 273. So again, I'm going to get that into Kelvin. Gives me 460 degrees Kelvin. And the question is, what is the new volume? And I always have my students at first year Chem, like I said in the last lesson, to make a prediction here. Well, if the temperature is rising, I would expect the volume to rise. And it's just a way to check ourselves. So now I'm going to use this gas law. So I'm just going to plug in the numbers. So I have 452 mils. I have 295 Kelvin. I have X over 460 Kelvin. So if I solve for X, so the units Kelvin cancels out, and I'm left in milliliters, which is what I want. So that what that gives me is, so V2 to 3 sig figs, 705 mils. And I said that if the temperature went up, the volume would go up, and that's what it did. And so, again, that is a problem that you guys would have done in first year Chem. But just to make sure, it's going to lead us into the other gas laws. Okay, now the next gas law, like I said, is about pressure and temperature. Okay, and again, you never need to know the names of these gas laws. This is called Charles' law. Here's the next one. This one is actually called Gay-Lussac's law. But again, you don't need to know that. But as temperature is increased, pressure also increases. And then that leads into, this is the gas law that there's two main gas laws, and this is one that you got to remember. This one is actually not on the formula sheet. And this is one that I think we need to know how to use. And it's not a difficult one to whoops. I messed up. Let me go back here. Sorry about that. Mr. Wood is not great with technology. Okay, so this problem here. Why did it do that? Maybe I'm not going to be able to do it. Okay, so again, so this gas law, the combined gas law, first year Chem, I just call it the pressures, the volumes, and the temperatures. And on this gas law, the units on pressure, they don't matter if it's ATM, millimeter, mercury, or torr, as long as they agree. And the same with volume. If you're milliliters or liters, as long as they agree. Okay, now we'll do this problem. And again, I'm going to do the same thing that I've done in the other problems, which is I am just going to list out everything. Sorry, I have these technology problems. So going back then, so we have, let me just go down here to the bottom of the board. So now we've got temperature and pressure, and just how they are qualitative related is if one goes up, the other goes up. And so we could, if we wanted to, we would have another gas law that would look like that. Well, if I take this gas law and then I combine it with these gas laws up here, what I get is called the combined gas law. And there's two main gas laws in chemistry, and this is one of them. When you put all this together, P1 times V1 over T1 equals P2 times V2 over T2. So again, this is the main gas laws. Here's one, and the other one is Piv-Nerd. And again, pressure, P1 and P2, the units don't matter as long as they agree. V1 and V2, again, the units don't matter, milliliters or liters, as long as they agree. Temperature, though, has to be in Kelvin. Okay, so I'm going back to the problem in the notes. And again, I'm just going to list out everything. So it says O2 occupies a volume. It says 1 liter. And this, too, is make sure the units are right. It says the temperature is 25 degrees Celsius. So again, I'm going to get that into Kelvin. And the pressure is 3.50 atms. And then it says calculate the new volume. So here's V2, and that is X. So here are the ones, V1, T1, P1. And it says at STP, and this is something else we're going to talk about in a minute. And this is review from last year. If a problem is at STP, that stands for standard temperature and pressure. It means that the temperature is 0 degrees Celsius or 273 Kelvin, and the pressure is 1 atm. So even though they don't list out numbers, they really gave us numbers there. So again, in first year Chem, I tell my students, this is the P's, the V's, and the T's. So now if I go back and I plug in the numbers, so P1, 3.5, V1, 1. And since this is in liters, my answer will be in liters. And again, it didn't have to be in liters. You just had to make sure that the units agreed. And there's temperature. P2 is 1. V2 is X. And T2 is 273. So the combined gas law. Okay, so then to solve for X, so I'm going to isolate X on one side. So I'm going to multiply both sides by 273, and I'm going to divide both sides by 1. Okay, and if I do that, and again, something I could have done at the beginning is to make just a qualitative prediction. Okay, what I get here is 3.21. And again, still always watching sig figs, always watching units. If I had made a prediction about what would have happened, if the temperature had went down, that would have forced the volume down. And if the pressure had went down, that would have forced the volume up. So we kind of have opposite effects here. And so you just have to see the ratio, how volume affects, or how pressure affects volume and how temperature affects volume. So, okay, the answer there, 3.21 liters. Okay, back to the notes. Again, a lot of review here at the beginning of this chapter, and gases are always a big deal. Okay, so here's where we were. Okay, the next thing is called Avogadros Law. And it says for any gases at a constant temperature and the pressure, the volume is directly proportional to the number of moles. Okay, so each balloon here contains 1 liter of gas at 1 atmosphere and 25 degrees Celsius. They each contain 0.041 moles. And this is really going to be an introduction into the ideal gas law, which we're going to talk about in a second. Okay, but what this is saying here, and this I don't think comes up in any of our problems, but N is the symbol that is used for moles. And I don't know why they do, but N is for moles. I guess M is being used for molarity, and so whatever. It's N is for moles. But what we're saying here is that if the volume goes up, the moles go up. Makes sense. If I blow air into a balloon, I'm adding molecules. Well, the volume gets greater, and it wants to take up more space. And And so what we get is this. V1 over N1 equals V2 over N2. Avogadros Law. Avogadros Law. The other point here that you should note, and I didn't really write this out, it's called Avogadros hypothesis. Avogadros hypothesis. But what it says is, it says equal volumes of gases at the same conditions what I mean by that is they have the same temperature and the same pressure. So going back to Pivner, which we're going to get into in a second, so then they would have equal number of molecules. When you think about P equals nRT, well, if we're saying the P, the V, and the T are all equal, R is a constant, well, then N would be a constant, which is moles. So Avogadros hypothesis, equal volumes of gases at the same conditions, being the same temperature and pressure, would have equal number of molecules. Okay, so then back to the notes where we were, just to make that point. Okay, and so that's what it says there. Each balloon contains 1 liter of gas, and at 1 atm and 25 degrees Celsius, so the same conditions, so the same pressure, the same temperature, equal volumes, they would all contain the same number of moles, which means they would all contain the same number of molecules. Okay, the next thing, in stoichiometry, when you guys were first taught stoichiometry, we said the coefficients were used to represent a mole ratio. So 1 mole of N2 plus 3 moles of H2 makes 2 moles of NH3. But if for gas stoichiometry, we can say the same for liters. So if we ever needed to do a straight liter to liter conversion, again, we could just use the coefficients. So what you can see what I'm saying here. 1 liter plus 3 liters makes 2 liters. And you should note that. So if you ever have to do a liter to liter conversion, you can do it that way. Okay, the next thing, this is something that you guys do not need to go through the derivation, but where the ideal gas law comes from. So Boyle's law, how volume is directly proportional to 1 over P. Charles' law, how volume is proportional to temperature. Avogadros' law, how volume is directly proportional to the number of moles. And here's the values for R, and I'm going to point this out. This is on our formula sheet, and we're going to use different ones over the year at different times. But the formula sheet, and I'll point this out here. You can just see me a little bit, but if you notice, the units on the bottom, Kelvin mole, are the same. The units in the denominator are different. And then, so if you put this all together, what you end up with is the ideal gas law. Okay, and so that's what's important here, is that's the ideal gas law. And I want to talk about what's on the bottom here too. So the ideal gas law only works when gases are relatively hot under low pressure and they don't bond to each other. Okay, so I want to kind of review that. Okay, so back to, so like I said, 2 main gas laws. And so erasing all this. So 1 main gas law, which consists of really 3 other gas laws. The combined gas law really consists of 3 other gas laws: pressure, volume, Boyle's law; volume, temperature, Charles' law; and then this pressure, temperature called Gay-Lussac's law. But the second one, and again, you don't need to go through the derivation of this, but the second main gas law is Pivner, and this is on our formula sheet, definitely something we will use So here's the formula sheet. So on the back, there's PivNert, and then here are the values for R. And like I said, like I was saying there when I had the notes up, the unit sheet and how that worked. And I wanted just to talk a couple things on that page. First of all, on the units, so the 8.31, which is for kilopascal times liters over Kelvin mole. And something just to note, it's something you can write down on your formula sheet, but a joule is equal to a kilopascal times liters, which really means you can write this out also as 8.31 joules over Kelvin mole. Okay, that's something to note, okay, because that will come down the line later when we're doing problems with joules. And then what I had on the very bottom of the page, I said the ideal gas law only works well when gases are relatively hot. So this is the conditions for an ideal gas. And what this means, what this really means, is that molecules, they don't bond to each other. They don't interact with each other. Number one is hot, or high temperatures. And to me, that makes sense because that means molecules are moving really fast and their chances to interact with each other go down. Number two is they're at low pressures. Well, again, that makes sense to me. If they're at low pressures and they're not being packed tightly together, they also will not interact with each other. And then what I didn't have down to number three is there's no attraction to each other, which will occur when we have nonpolar molecules. So nonpolar molecules have such a weak intermolecular force, they're not going to bond with each other. And then smaller molecules too, smaller molecules, because they have a weaker intermolecular force versus larger molecules. So what I'm saying here, what I'm trying to say, not saying it very clearly, is these are conditions where gases will behave ideally. So when they're hot, because the molecules are moving so fast, they're not going to want to interact with each other. At low pressure, so they're not compressed, and they don't have attraction between each other. So when something is non-polar, and the smaller molecules are, something we're going to talk about later, the smaller they are, the weaker their intermolecular forces, the less they have a chance to interact with each other. Okay, so again, a lot of review here. This whole chapter won't be a review. We're going to get into some what were pretty good first-year chemistry problems and some AP problems too. Okay, so now back to where we were. And again, the derivation of PivNert you don't need to remember. And the value for R you don't need to remember, and even PivNert. And on this, though, the units, it's real important, is that the units, I said on the combined gas law, the units on pressure and volume, as long as they agreed, everything was okay. But on PivNert, pressure has to be, well, I guess the volume has to be in liters, the temperature has to be in Kelvin, and pressure, whatever the units of pressure are, determine R. And that's important to note. Okay, so here's a problem. Again, from first year Chem. Okay, so again, I'm going to just list out everything it says. So calculate the grams of H2. Whenever grams are involved and it's a gas law problem, I know, again, there's two gas laws. Okay, there's two gas laws. And whenever a problem has grams or moles in it, then I know it's got to be a piv-nert problem. Okay, so again, since this problem is asking about grams, this has to be a piv-nert problem. So again, just what I said before. So the units on piv-nert, volume has to be in liters, temperature has to be in Kelvin, and then the units on pressure depend, or the value for R depends on the units for pressure. And that's where we go back and we look at the different values for R, which are on our formula sheet, which you don't need to remember. Okay, so again, I'm going to list everything out. So we're trying to find grams. We have the volume is 8.56 liters. The pressure is 1.5 ATMs. And the temperature is 0 degrees Celsius, so it's 273 Kelvin. Okay, so it's got to be a piv-nert problem. And if I'm trying to solve for grams, what I'm really going to solve for here is moles. So once I know moles, I'll convert to grams. So I've got PV equals nRT. So again, to me, it's really just plug and chug with the conversion here. So since pressure is in ATMs, now I'm going to go back to the formula sheet and I'm look over here for the value for R. And since the pressure is in ATMs, I want to use the 0.08206. So the pressure is 1.5 ATMs. Watch how the units work. The volume is 8.56 liters. N is X, moles. And then R, so it's 0.08. I always do this. I go 0.0821. And the units are liters over times atmospheres over moles times Kelvin. And then the temperature is 273 Kelvin. Just like I will all year long, I want to show you how the units work. So if I'm solving for X here, so I'm going to just divide the numbers off just to save writing. But over here, I'm going to write in the units. So I'm solving for X. So Kelvin goes, liters go, ATM goes, and I'm left moles, which is what I want it to be in. Okay, so if I do the math, 1.5 times 8.56 divided by 0.0821 divided by 273, what I get for X, or for N, is 0.57 moles. The question here was grams. It asked for how many grams of H2. So now I need to do a conversion. So 1 mole hydrogen, it's listed out too. Hydrogen is one of those diatomic elements, so its mass is 2. And so what that gives me is 1.14. My sig figs are off. I think I had 2 sig figs. So really to 2 sig figs, 1.1 grams of H2. So again, getting into some problems that, again, all that is review, problems that we have done before in first year chem. So, okay, I think that is a good place to stop, and we're really going to start moving into new stuff. And I am going to post a lesson for Friday, and again, this might be really good stuff to be doing over fall break, just to kind of, because we're going to come back and we're going to do a lab. We're going to wrap up chapter 5, and so it'll be not the first week, and I don't know the second week, but not very long after we get back, we're going to have test on 5. So, all right, guys, talk to you soon. Bye.